So in the past, what we ended up doing for unsupervised learning was learning these generative models. So we talked about generative discriminant analysis as well as the naive Bayes model. And today we're going to talk about a mechanism to enable us to learn structure in data without using any labels whatsoever. And so most of our focus has been on supervised learning in this class. And today we'll start talking about unsupervised learning. And so this week is going to be a topic called dimensionality reduction. And what dimensionality reduction is a mechanism for us to go from the original data that we have, which is in d dimensions, to some smaller dimensional space where k is less than equal to d. And so we'll cover a topic known as principal component analysis. And this is a linear dimensionality reduction technique. That's going to be much of the first half of today's class. And in the second half, we'll talk about nonlinear methods. But it's really worthwhile to know why you should care about unsupervised learning. So imagine you are a household user of many, many electronics, and you look at the readings on your power meter as a function of time. So the y-axis is watts consumed, and the x-axis is time. And what you really want to know is not what's the total wattage, but rather how does that break down? How does this time series data break down across many, many different appliances that you might be using at home? How does it break down over the lighting, the use of a dishwasher, refrigerator, etc.? And you might want to do this without having access to labels. You might not want to have someone go annotate in time anytime they use the dishwasher. And so in order to do this, there's really, really powerful classes of unsupervised models called probabilistic graphical models. So for those of you who are planning to take CSC 412 in the next iteration, so next year, you'll learn a lot about these classes of models and how you can use them to do unsupervised discovery of latent structure in your data. So whenever we say latent, what we mean is that the structure is posited or believed to exist. And it's the goal of these models to try and uncover it from the observations. And so this is also true when we think about structure in things like documents. So there's a really nice paper called Finding Scientific Topics by Griffiths and Stoivers. And what they essentially do is give an unsupervised method to take large corpuses of documents over time and figure out what topics change, how they change, and how their relative fractions increase and decrease over time. So this enables them to do two things. It enables them to find topics that exist in many, many documents, and it enables them to answer the question of how these topics change in terms of their relative importance across time. So there might be, for example, a topic like number 37, which seems to characterize questions around amino acids and proteins that seems to diminish over time in the collection of documents that they have, versus a topic like climate change, which is probably what you might guess these words all correspond to. And that's a topic that seems to be growing more and more important starting from about 1991. And again, this was done without the use of any labeled data, again using a much, much more complex tool called a probabilistic graphical model. And so today, we're going to cover a much more simpler way to learn latent concepts or latent structure that exists in data. And we'll cover dimensionality reduction today. And in about 2 weeks, we'll cover another topic called clustering. So those are the two you'll learn about in the context of CSC 311. So what exactly is dimensionality reduction? It's a really, really simple way to say that I'm interested in taking the high dimensional data that I have and mapping it or learning some kind of a mapping function to turn that data into a low dimensional representation. And so this lecture will talk about linear dimensionality reduction. So as a concrete example of this, let's imagine that you're a psychologist who's interested in modeling and studying variation in human personality. And so you might go about this enterprise by taking a survey and asking lots and lots of people over the internet or in classrooms questions. And you take the answers to those questions and try to find out the latent structure that existed and how people responded to those questions. So let's say they were all binary questions, yes, no questions. So you'd have a d-dimensional vector of binary data, And what you really wanted to know is, does there exist some latent structure in the answers that humans gave to these questions? And can that latent structure actually be useful in telling me things about human personality? Because you might believe that within each individual, they have notions of variation along different axes. So someone might be an introvert versus another individual might be an extrovert. Some might be much, much more outgoing. Some might be much more withdrawn. Some might have a lot of energy, some less. And all of these might manifest in the answers that they provide to these questions. And so your goal in this structure discovery or latent structure discovery is to try and find out what are these axes of variation and how do they actually change across the humans that I have in this survey data. So a linear dimensionality reduction technique called factor analysis was actually proposed about 40 to 60 years ago. And essentially, in that context of that study, they found what they call the big five, which are things like extroversion, agreeableness, openness to experience as a consequence of doing this actual experiment. They found 5 different sources of variation that humans who took their survey data actually varied along. And so today we're going to consider a very different but very closely related model called principal component analysis, and it's going to be a linear dimensionality reduction technique. So all those words are important, as you'll see, but PCA is also going to be our first unsupervised learning algorithm. So thus far in this class, we've said that we're working with a data matrix that's Rn by D and a target matrix that's Rn by 1. When we're doing supervised learning, so now that we're doing unsupervised learning, we're only going to be working with this data matrix that we have. And our goal is to identify latent structure that exists in this data matrix. So in dimensionality reduction, we find this structure by solving the problem of mapping from data to a lower dimensional space. So the argument is that if you can successfully map your original data, which took D dimensions, into a lower dimensional space, and I haven't defined what constitutes success here, but if you are able to do that task successfully, the intuition you should have is that you can only do so successfully by compressing that data along most of the interesting ways by which that data changes. You want to preserve all the information content in that data when you do this mapping onto a lower dimensional representation. And so that's the task that we're going to try to solve. So in the context of this particular data set, you have 3-dimensional data. And if we want to map to a lower dimensional manifold, we need to map to a plane or a line. So 2D or 1D. And in this particular case, we're going to map to a 2-dimensional plane. What does it mean to project data in 3D onto a 2-dimensional plane? For each point, we're going to take it and find the projection of that point onto the subspace that we cared about. And then we're going to plot it, and that's what's shown on the right-hand side. So I'm going to pause here to see if folks have any questions about what dimensionality reduction actually is and what this figure is actually showing. Yeah? How do you choose the plane? Yeah, so that's going to be what we talk about in the next slide. So we haven't gotten to that yet, but we'll get to that in a bit. Any questions about just the concept of reducing dimensionality and why it's important? So we might want to do it to save computational memory. We might want to do it because we think we can remove irrelevant features and thereby reduce overfitting for machine learning models. And we might want to do it just because it's easier to visualize things in 2D than it is in 4D or 7D. Okay. So if you at least think the premise of mapping onto a lower dimension is useful, let's now think about how to solve that problem. And when we start thinking about how to solve that problem, it's easiest to think about it in the simplest case possible, which is mapping from a 2-dimensional space onto a 1-dimensional subspace. And this is something that you might have all seen in your linear algebra classes, and this goes by the name of Euclidean projection. So when we want to project onto a 1D subspace of 2D, what do? So remember, a low dimensional subspace of 2D is a line. subspace S is the line along the unit vector u. What does that mean? Every line in two dimensions can be represented by a unit vector u, which tells you the direction of the line, and a scalar z, which tells you the magnitude of the point on that line. So if z was 1, you would represent this point. If z was 2, you might represent this point. If z was 3, this point. If z was minus 1, it would be this point on this line. So any point S can be written as z times u for some choice of z. So that's how you would represent any point along this subspace of 2D S, which is this line, once you have the unit vector for that line. So any questions about representing points in this subspace? It's done via the use of a vector that represents direction and a scalar that represents the magnitude of the vector. Okay, so now we can talk about what the projection of any point in 2D looks like onto this subspace, which is this line. So the projection of vector x on a subspace S is denoted as this projection operator of x onto S. So you'll recall from linear algebra that if you wanted to think about what the dot product of two vectors is actually doing, you can write the result of that down as norm x, norm u cosine theta, where theta is the angle between the two vectors. And so that's just equal to norm x cosine theta, because we're going to assume that u is a unit vector. So it has norm 1. And geometrically, what's happening is that we're taking the length of this original vector, the norm of this vector, and we're multiplying it by the cosine of the angle between the vector and the unit vector of the subspace. And what that does, if you'll recall from your trig classes, is that it gives you the size of the vector projection. And once you have the size, you just multiply it by the direction to obtain the projection of x onto S. So that's how you take a vector in two dimensions and project it onto a line. You just do the dot product with the unit vector to give you the magnitude, and then you multiply by the unit vector again to give you the direction. Any questions about this slide? Okay, so now we're going to jump into higher dimensions. And the jump into higher dimensions is going to express the idea of projecting onto a k-dimensional linear subspace and how we do that. And we're going to assume that we start from some d greater than k space. So the idea in the one-dimensional case was that we needed this unit vector. This unit vector told us the direction of where the subspace was, and then by multiplying the unit vector by a scalar, we could represent any point in that subspace. But now that we're in 2D or 3D or n dimensions or k dimensions, we can't just use a single unit vector. We need to be able to use multiple unit vectors. We want to be able to write down a mechanism to express any point on that subspace. So for a general k-dimensional subspace, we know that we can write any point, let's call that M, as alpha 1 times u1 plus alpha 2 times u2 plus ... alpha k times uk, where u1 and uk are an orthonormal basis for that subspace. So think back all the way to the math quiz and from your linear algebra classes, you know that if you have a k-dimensional subspace, then you can represent any point on that subspace as a linear combination of an orthonormal basis, of a set of orthonormal basis vectors. And so we're going to let this set of u be an orthonormal basis for the subspace. That is, all of these are unit vectors and they're all orthogonal to each other, which means that u1 transpose uk for all k not equal to 1 is equal to 0. And so once we know how to represent any point on a subspace, what we're going to do is essentially do an Euclidean projection onto each of the basis vectors for that subspace. So we're going to project onto each of the unit vectors individually. Just as we did in the one-dimensional case in the previous slide, we're going to do that one at a time for all of the unit vectors. And what that's going to give us is a magnitude. It's going to tell us just how much this point moves along that unit vector in that direction within that subspace. And we're going to multiply that magnitude by the direction given to us by the unit vector. And we're going to do this for all of the dimensions. And then we're going to sum it up. And that summation of weighted combinations of unit vectors is what's going to represent this projection. So mathematically, this projection of x onto S is going to be given to us by a summation over k unit vectors, where each of the magnitudes of how much that unit vector changes is going to be x transpose ui. So we're doing k different one-dimensional projections onto each of the unit vectors corresponding to the orthonormal bases for this subspace, and then we're going to just sum them all up. That's how we're going to represent the projection of any vector x onto this subspace as a linear combination of how the unit vectors change within that subspace. Any questions so far? So this is just defining the projection in k dimensions. Yeah?
So what exactly is the matrix U? Is it like the orthonormal basis like in R?
It is an orthonormal basis in, so U is going to be an a D by k dimensional matrix. Yeah. And so it's each of, so we have each UI is in RD. And we have k such UIs. So when you pack them together, you get a D by k dimensional matrix. And so that's exactly what this matrix U is doing. Or k by d, depending on how the notation sets up. Yeah?
Sorry, would the D here also not be k? Because we're dealing with a k-dimensional subspace?
No. So each of the orthonormal bases is represented in the original dimension. So when you take a vector in RD, you need to be able to do this dot product. So each UI lies in RD. And there are k such UIs, because you need k of them to represent all of the space within the subspace.
So all the, like, from k to d, all those things would just be zero, because we don't want anything in those dimensions if we're representing the subspace for k.
That happens in very special cases where your subspaces are parallel to the orthonormal basis of your original space. But it doesn't always have to be, because you could have a plane that's at a 45-degree angle, and then you won't have any zeros in there. Okay. And so you can write down Z, which is going to, remember, this Z is going to be a k-dimensional vector. And each Z sub k is going to be the strength of how much this projection is going to be represented within the kth orthonormal basis vector. So just as a cartoon diagram here, I drew these sets of points. So these are all points in R3. And if we wanted to project them onto this linear space, S, which is spanned by two basis vectors, U1 and U2, and these are going to be orthonormal to each other, so they're at a 90-degree angle, and they're all unit vectors, then you can represent any point that lies on this subspace as some linear combination of alpha 1 U1 plus alpha 2 U2. And to calculate the projection of x onto the subspace, we just need to find what is the value of alpha 1, or in this case Z1, and consequently alpha 2 or Z2, that represents the strength of the projection of this point along each of the unit orthonormal basis vectors. And to get Z1, we're just going to do U1 transpose X, and Z2 is going to be U2 transpose X. So any questions about projecting onto a k-dimensional space? Okay. So far, one of the assumptions when we talked about this that we made was that the line or the space passed through the origin. So in general, you can avoid this situation of passing through the origin by working with what are called affine spaces. So affine spaces are basically linear spaces in d dimensions or k dimensions that move around. And you can move the space up and down by adding any arbitrary vector. So if this was the origin, we were previously assuming that all spaces sort of just existed and rotated around the origin. But I can represent the space equivalently as this space as long as I add mu hat, some vector that just shifts where the space is located. And so when you do this addition, it's called an affine space. And so this affine spaces enable us to have an arbitrary origin mu hat. So we move from shifting on to subspaces that intersect with the origin to thinking about shifting to projecting on general affine spaces. And if we have general affine spaces that are characterized by this mu hat, then it's still really easy to know how to project onto them, because the projection operation is given to us by u transpose x minus mu. And each of this gives us a k-dimensional vector where, again, each element of z tells us just how much this projection, where this projection exists as a function of each of the orthonormal bases of this affine space now. So in machine learning, there's many, many times you'll start seeing this idea of a reconstruction, which is taking some data point, putting it through some computation, and getting out a reconstruction. And so this projection can be thought of as this reconstruction of this point on the projected subspace. And so we'll use x tilde and call it the reconstruction of x. And we'll use this term z, and we'll call it the representation or the code. Why do we call it the representation or the code? Is because it's a new system to describe how this point behaves. It is a representation of this point, not in the original ambient space, but rather in the space spanned by the orthonormal basis of this linear operator, this matrix U. So remember a few weeks ago when we did our linear algebra review, I told you about the idea that matrices are these cool things that like warp space. They take your original space and then they push points through it, and since they're a linear operator, they scale and stretch and shift these points. And that's exactly what's happening here in this representation. You're taking any point and you're representing it in a new space. In this case, the space of your subspace that you've chosen. So all of this is to say that if we have a k-dimensional subspace in a d-dimensional input space, then for x in Rd, we can pull out a z in Rk, the representation of the code for any given point. It's the equivalent representation of how the projection of that point behaves within that subspace. And if the data points x all lie close to their reconstructions, then the space is useful because we can start approximating distances not in the original d-dimensional space, but rather in the much, much smaller k-dimensional space. And so when k is less than d, it's much cheaper to work with z than it is to work with x. So it's easier to work with the projection or the reconstruction of x than it is to work with the original data point x. And so a mapping to a space that's easier to manipulate or visualize is called a representation, and learning such a mapping is called representation learning. And when you go on to study more advanced topics in deep learning, you learn about many, many different ways to learn representations. And we're talking about the very simplest concept of representation learning here, which is a linear representation. So I'll pause here to see if folks have any questions. Yeah.
So is x tilde the point in our k-dimensional subspace?
That's right. So in this k-dimensional subspace, you can write down x tilde as some, z1 times u1 plus z2 times u2. But remember, like, this projection can also be written out in terms of like the orthonormal basis for the original space as well, because it's a subspace of that original space. Yep. Great question. So this question, so I'll repeat the question, which is, do we lose any information in the reconstruction operation? What do you think? So in general, you do lose information when you do this operation. There are special cases where you don't. Like so let's say, we're operating in 3 dimensions right now, and all of our points lay on this keyboard. If we project onto a 2-dimensional space that was flat and parallel with this keyboard, then my claim is we don't lose information. But in most general cases, the projection onto a k-dimensional subspace is a lossy representation. And so the question then becomes, how do you choose this subspace? So I told you how to do this projection operation. Now I'm going to tell you how to choose the subspace that corresponds to some notion of a good representation. So we're going to have and start working with our data set now. So remember, our data matrix is some x, which is a matrix in our n by d. We're going to call mu hat the empirical mean of the data. So that is some d-dimensional vector that represents the mean of the original data. And now our goal is to choose a d by k matrix U with orthonormal columns. And this is going to be our unsupervised learning problem. So in supervised learning, we created this loss function. We use gradient-based descent methods in order to learn the parameters of our predict supervised model. But now we have this unsupervised representation learning problem. We need to find the elements of this matrix U, this d by k matrix U, that represents some notion of a good subspace. So those are the parameters of this learning problem, and we need to find what those parameters are. So we need to think about what a reasonable cost function or loss function might be. And so, your colleague asked this question of, do we lose information? And maybe we can use that idea to guide the design of the first cost function, which is that a good subspace might be one that minimizes reconstruction error. So to minimize reconstruction error, we're going to try and minimize over the space of all matrices U that have orthonormal columns the summation from I is equal to 1 to n of the average of the L2 distance between every point and its reconstruction on the subspace. So remember, if I have a bunch of points, every point here is the original point in blue, and every point here is the reconstruction in red. And what this cost function is really doing is it's looking at the distance between the squares and the circles. It's squaring that distance, and it's summing them up. And it's saying that in order to find a good subspace, you need to move your plane around in your low dimensional space in such a way that you minimize reconstruction error. And that's what this objective is saying. Another possibility from the perspective of maximizing information content preserved might be to maximize the variance of the reconstructions. So going back to this plot, each of these blue points are now data that lie on some subspace. For these data, we can ask, what is the variance of this data? Because remember, we know that projecting onto a lower dimensional space is a lossy transformation. So to minimize the amount of information lost, we might want to maximize the amount of variance in the projection. And so to maximize the amount of variance in the projections of the reconstructions, the goal is to find a subspace where data has the most variability, which is to say that x tilde I minus mu hat norm squared summed and averaged of all the data points is as large as possible. So we're maximizing over the matrices U with orthonormal columns. So any questions about what these objective functions are saying? Are folks comfortable with them? Yeah?
So the x tilde, that one is like in d dimensions when we take the difference?
Yes, so x tilde I is also in d dimensions because it's the projection. And so it turns out that both these two criteria are equivalent. And what we're going to do now is to show you that the cost function corresponding to minimizing reconstruction error is the same as the cost function corresponding to minimizing the variance of the reconstructions, or rather maximizing the negative of the variance of the reconstructions, or rather maximizing the variance of the reconstructions. So to prove that, we'll show that this left-hand side is equal to some constant that's not going to change as a function of u minus of this right-hand side. So if you reduce this, then this also goes down, which means that the negative of this goes up. How do we show that? So this is the definition of the reconstruction, which is mu hat plus uzi, where zi is the code vector for each xi. And this is the definition of how to get the code vector, which is you take u transpose of xi minus mu hat. And so the first observation we're going to use is that because the columns of u are orthogonal, u transpose u is the identity matrix. And so the difference between x tilde minus mu hat norm squared can be written by pushing this term in here. So we're going to substitute for x tilde I in here. And what that's going to give us is that the mu hat and mu hat cancel, leaving us with uz. So then we get uz norm squared can be written as z transpose u transpose uz. And we'll note that u transpose u is the identity matrix. So we get z transpose z, which is the definition of z norm squared. So this is saying that the norm of the centered reconstructions is equal to the norm of the representations. The second observation we'll need is that the difference between the reconstruction and the mean and the reconstruction and the original data point has a 90-degree angle. So remember, what does it mean to have a difference of two vectors? When you take the difference of two vectors, you basically get the arrow that points from one point to another. So geometrically, if you have these 3 points, this is your reconstruction, this is the mean, and this is the original data point. What we're trying to prove here is that the difference between x tilde and mu hat, which is this vector, and the difference between x tilde and the original point, which is this vector, have a 90-degree angle. And to prove that something in high dimensions has a 90-degree angle, you would show that the dot product of the two of them, of the two of these vectors, is 0. Because remember, the dot product of A transpose B is equal to 0, which implies that cosine theta is equal to 0, and so you invert the cosine function to get 90 degrees out. So let's actually just write down what the dot product is. So this is just the first vector, and this is the second vector. And we're going to substitute in here the definition of the reconstruction, which is mu hat plus u transpose of xi minus mu hat. So that gives us this term on the right-hand side. Next, what we're going to do is take each of this as A and distribute it over these two terms within the second braces. So we'll get this as our first term, and then this times this as our second term. And you'll note here that a simplification has been made, because if you just multiplied the top two circles, what you would get in the middle of those top two circles is u transpose, u transpose. But remember, u transpose u is the identity matrix, which is what allows you to simplify it to just u transpose. And now you'll notice that this term is the same as this term, with the only difference being a negative sign. And so the two terms cancel out, and that gives you 0. So if the dot product between these two is 0, it means that these two vectors are orthogonal. So we'll see why these two observations are interesting. Because what Pythagoras' theorem tells us is that if I have two orthogonal vectors, then I could take And those vectors are A, B, and C, where C is the vector that represents the endpoint of the other two that I know to have a 90-degree angle, then I know that A squared plus B squared equals to C squared. And I'm just applying that operation now in terms of vectors that are differences between these 3 points that I care about reasoning in. And if I apply that identity, which I can do so because I've proven in the previous page that these two vectors are orthogonal, and I sum these terms over from 1 to n and take the average of them, then I get this identity here. So going from here to here is summing and taking the average over I is equal to 1 to n. And now let's just look at each of these three terms that we've ended up with. So the term on the right-hand side is a constant with respect to u, because it only depends on the original data and the mean. So u doesn't show up anywhere on the right-hand side. The first term is the difference between the reconstructions and the mean. So this is the projected variance. And the second term is the difference between the original point and the reconstruction, which is the mean squared error, which is the difference between what happens between the original data points and their projection. And so if I take this from the left-hand side to the right-hand side, I get the identity that the projected variance is equal to some constant minus this reconstruction error, which concludes the proof that maximizing the variance is equivalent to minimizing the reconstruction error. So let's take a step back. We started out by saying we wanted to solve unsupervised learning in this problem. We said that a reasonable cost function is either to maximize the amount of information preserved in the form of the variance of the reconstructions, or to minimize the distance between the reconstructions and the original point. What we did in the last few slides is to show that those two objectives are one and the same, which is to say it doesn't matter which one you pick, you'll get the same answer. And now what we're going to do is think about how to solve the problem of maximizing the variance of the reconstructions. Because we need to solve that problem in order to identify a good subspace for us to project our data onto. So choosing a subspace to maximize the projected variance or minimize reconstruction error is exactly the algorithm that we'll talk about now, and it's called principal component analysis. So we're going to start out by considering this matrix called the empirical covariance matrix that we reviewed when we talked about Gaussian discriminant analysis. And so this is just the outer product of the difference in means averaged across all the data points. So sigma hat is a symmetric and positive semi-definite matrix. And what that means is that you know that all of the eigenvalues of your covariance matrix are non-negative. And that's a property we'll make use of when we think about how to learn this matrix U, our projection matrix. So the optimal PCA subspace we're going to show is spanned by the top k eigenvectors of sigma. What does that mean? More precisely, we're going to choose the first k of any orthonormal eigenbasis for our covariance matrix, and we're going to call that the projection matrix that we work with. So remember, sigma hat is in our d by d. Sigma hat, by virtue of being a symmetric positive definite matrix, exhibits an eigendecomposition by the spectral theorem, which means we can write sigma hat as Q transpose lambda Q. And you remember that the columns of Q are the eigenvectors of the empirical covariance matrix, and this lambda is a diagonal matrix where the elements along the diagonal are the eigenvalues. And what this statement is saying is that if you wanted to find a matrix U that lay in k dimensions, then the best thing that you could possibly do to find that matrix is to do an eigendecomposition of your covariance matrix and pick the eigenvectors corresponding to the top k eigenvalues, corresponding to the largest k eigenvalues. So that's me giving you the solution for how to find this matrix U. So any questions about the actual statement of the solution? I haven't given you an intuition for why it's the right thing to do yet, and I will in a minute, but I just want to make sure that everyone understands what I just did. Yeah?
So when we have the empirical covariance matrix, are we assuming that it already kind of standardized our features?
You can center the data before calculating the empirical covariance matrix if you wanted, and then you would just be projecting onto a subspace, and you'd have the mu as like an affine space, so you know how to do that projection if you need it.
So will PCA be assuming that it is a base level correlation between their data?
It makes no real assumptions. Like, remember, PCA is trying to find a subspace that minimizes the reconstruction error. It's not making any distributional assumptions about how your features are related to one another. It's just telling you that it can give you the algorithm that minimizes the reconstruction error, whatever that looks like. If your features are completely independent, then there might be no good subspace to project onto. And in that case, it might give you just some random linear subspace because it can't do better than any projection altogether. But usually, if you have data that you think has structure, it's not going to be the case. Okay, so any questions about how to actually solve the problem of PCA? So you get your data, you compute this empirical covariance matrix, you do a spectral decomposition of it, you find the eigenvectors of the top k eigenvalues, where by top I mean the largest, and you use those as the columns of your matrix U, and you're done. So why is this the right thing to do? So just as an aside, these eigenvectors are going to be called the principal components. And so by analog to the principal axes of an ellipse, these are the principal components along which your data vary. That's why it's called principal component analysis. So to derive why that's intuitively the right thing to do, I'm going to show you the case for k is equal to 1. So the case where you need to find a single vector that's going to represent a unit vector that enables you to project all your data onto. So for k is equal to 1, we are fitting a unit vector u, and our code is a scalar, zi, that's going to be given by u transpose xi minus mu hat. So remember, we're projecting onto 1D. This is a Euclidean projection. So we take our data, we subtract the mean, and we do the dot product with u, and that's how we get the code or the representation in this one-dimensional space. Now we're going to maximize the projected variance, because that's the loss function we care about. In this case, it's a cost function we care about maximizing. So the projected variance is x tilde I minus mu hat norm squared. I'm going to substitute this with zi, because I proved in observation 1 that the variance of the projections is the same as the norm, the sum of the norms of the reconstructions. So that's using observation 1. And I know zi is u transpose xi minus mu hat by the definition of what the representation is. And so going from here to here, what I'm going to do is just write out the square using this identity. So A transpose B squared is A transpose B, B transpose A. So that enables me to write this out as A transpose B, B transpose A. Next, I'm going to move this summation inside here and move the U and the U transpose outside the braces. So it's just changing the order of operations between the dot product and the summation over all the n data points. So I get U transpose of whatever this summation is, U. The quantity on the inside is the definition of the empirical covariance matrix. It is the sum of the outer product of all of the difference between the means for each data point. So I'm going to substitute that as U transpose sigma hat U. Next, I know that covariance matrices are symmetric and positive semi-definite, which means I can use the spectral decomposition theorem to substitute that as U transpose Q lambda Q transpose A, Q transpose U. And then I'm going to just define my vector A as Q transpose U. And so that's going to be A transpose lambda A. And this is a diagonal matrix. And so I can write this down as lambda J aj squared and the summation over the d dimensions of my matrix lambda. So this is just using the definition of the fact that lambda is a diagonal matrix. So now let's just stare at this term for a bit. Our learning goal here is to fit a single vector u. I need to pick one vector u. And it has to be a unit vector. And it has to maximize the quantity on the left, which is the same as maximizing the quantity on the right. So what vector should I pick that would maximize the quantity on the right? So I know that, let's say we had 3 elements in D, so we had a 3-dimensional space, then I would get lambda 1 a1 squared plus lambda 2 a2 squared plus lambda 3 a3 squared. And I have to pick one element u. So I'm going to pick the element u from one of the columns of Q. And I'll choose the column that corresponds to the column with the largest eigenvalue, or the eigenvector with the largest eigenvalue. Because when I do that, then it ends up, so if we want to maximize A transpose A, which is maximizing this quantity on the right, for some A is equal to Q transpose U, then we can assume that each of the lambda i's are in sorted order. And since U is a unit vector, A is also a unit vector, because A transpose A is equal to U transpose Q, Q transpose U. And that means that the summation of all the ij's is equal to 1. And so we can set A1 equals plus or minus 1 and aj is equal to 0 for the one that we don't select. And effectively, you can prove using just a sequence of simple arguments that the best you can possibly do for the right-hand side is to select the eigenvector corresponding to the largest eigenvalue. And that's the case for k is equal to 1. And we won't show the extension of this proof, but it's not a difficult proof to follow. So if you're interested, just send me a message and I'll tell you where to find it. But it's a really simple argument of you first take the first principal component and you subtract off the variance explained by the first principal component, and then you analyze the residual. And you'll find that analyzing the residual leads you to picking the second eigenvector as your next choice. And then by induction, you can show that that's true for all k. So that's the proof sketch. But intuitively, this is a really cool result. It's saying that if you wanted to minimize a reconstruction and you care about learning a linear subspace, you can do no better than taking your empirical covariance matrix and doing an eigendecomposition with it, and then picking the eigenvectors for the top k eigenvalues. And so it's a really neat algorithm that ties together ideas from how matrices and subspaces behave with each other. And it also ties together the idea that these eigenvalues aren't just numbers you learned about in linear algebra. They have meaning in terms of what they're doing to high-dimensional vectors. And so for this reason, I really, this is one of my favorite machine learning algorithms because it's so simple and it gives you a lot of intuition about how high-dimensional geometry behaves and how low-dimensional structure behaves within that context. And how matrices are sort of this really simple way to imagine translating between low and high-dimensional spaces. So to recap, dimensionality reduction aims to find some low-dimensional representation of data. PCA is going to project the data onto a subspace which maximizes the projected variance or equivalently minimizes the reconstruction error. And the optimal subspace is spanned by the top k eigenvectors of the empirical covariance matrix. And so because you are projecting data onto the space that is spanned by a set of k orthonormal basis vectors, each of the representations for your data points now have decorrelated features. So each of the k dimensions of Zi are by definition going to be decorrelated. Yeah? That's a great question. So k is a hyperparameter for this unsupervised learning algorithm. And so in practice, what people often do to choose the value of k is that they make a plot. On the y-axis of the plot is the reconstruction error or the variance or the negative of the variance explained. And as you can imagine, if you just have k is equal to 1, you have you explain some amount of variance. As you go to k is equal to 2, you explain more variance. So, sorry, this is the residual variance that is unexplained as a function of k. So as you go and pick more and more features, you'll find that they explain more and more of the total variation in your covariance matrix. But at some point, this curve begins to level off, because most of the variation in your data is going to be explained to you by the top 5, 10, 20 eigenvectors. And it's really after that it starts to represent noise. And so you pick k once you see this sort of elbow forming. So you try to find something that trades off between k being as small as possible but explaining as much of the variation as it can. Yeah. Why do you not use any you would plot this on the validation set. Yeah. Because the validation data also lies in RD, so you can take whatever you learn and then just project the validation set data into the lower dimensional space. Yeah. Hey.
Yeah. Once we apply PCA and we have like a lower dimensional representation of our data, what we do with that like representation, is that kind of based on the problem we're solving?
It's based on the problem you're solving. So what you will see later as to why mapping data onto a lower dimensional representation is a useful learning principle, because it's the basis of a lot of latent variable models, and we'll talk about a simple example of matrix completion in a bit. But the other reason is that let's say you had lots and lots of unlabeled data and very little labeled data. So if you wanted to learn a classifier, the classifier has to solve this task of mapping data onto some low dimensional representation that's useful for classification. But if you don't have a lot of labeled data, you can't solve that task well. So you could use something like PCA to get a good representation to start with, and then use that representation to fine-tune a classifier afterward. So that's one common use case. And that idea of combining unlabeled and labeled data goes under the name of semi-supervised learning. Okay, so if you ran PCA on actual high-dimensional data, what would you find? So if you ran it on a data set of faces of 19 by 19 grayscale images, it turns out with just 3 components, you can get pretty good reconstruction of what a face looks like. And so if you had your original data, which is 361 dimensional, which is 19 times 19, for face recognition, PCA with 3 components, so you take your data, you run PCA on it, and you map from 361 dimensions to 3 dimensions, and you train a classifier on that n by 3 dimensional matrix, then that already gives you 79% accuracy. And that's compared to a Gaussian mixture model on the original data, which gets you about 76.8% accuracy with about 84 states. And so we'll cover Gaussian mixture models later. So that's a pretty dramatic improvement for this very sparse projection. And so there's this experiment and a really famous paper called eigenfaces. So instead of eigenvectors, you have eigenfaces, because you can represent each of your eigenvectors as a face, and you can visualize what they look like. So you learn a k-dimensional, you take your data, you compute the empirical covariance matrix of it, you run an eigen decomposition, and you look at the eigenvectors and you plot them as faces. And so you'll see here that these are sorted by the eigenvalues, and as you go from top to bottom, you get more and more, you get less and less features showing up as prominent, and by the end, it kind of starts to look more like noise. So most of the structure in what constitutes a face is represented by the top k eigenvalues. And you can do the exact same thing for MNIST digits as well. So let's take a 5-minute break, and we'll come back at 2:10. Yeah.
We're planning to do something related to reinforcement learning.
Yeah.
I was just wondering if that would be like too out of the scope for this person.
No, you can explore it. If especially like again, like we didn't want to stop you from exploring things you were interested in, so go for it.
Okay. Would that be kind of like covered in later parts of?
We'll have one lecture on RL at the very end, so it won't be till the very end, which is unfortunate, but sometimes there's a U of T class on RL that gets taught.
Okay, sounds good.
There are lots of open source resources. What I recommend that you do is if you are doing an RL project, the biggest problem is that like RL projects take a while to get like working because you have this, I don't know if you're planning to build your own simulator or you have one or.
So like we don't have anything fixed. It's either we're gonna go to like traditional like game route or something related to finance. So
Yeah,
those
I think if you wanted to study like different RL algorithms on a finance simulator, that would be fine.
Okay. Just,
Or a game simulator.
Yeah.
Honestly, whatever you can get working is totally fine with us.
okay. Sounds good. Thank you.
The only thing I would say is that in terms of like actually when you write your report, you should just be clear about what constitutes success. Whenever you're building a learning model, you have some notion of what constitutes success.
Yeah.
Just make it clear what that is, and we should be fine.
On the report that's due on Friday or like
Final one.
Final.
For the report just due on Friday, just tell us what you decided to do.
idea. Okay. Sounds good.
Yeah, thanks so much. Okay, so we're going to get started again. We'll talk about two more interpretations of PCA that have really interesting generalizations. One of them is going to be called matrix factorization, and the other one is going to be called an autoencoder. And so that's going to be a form of nonlinear dimensionality reduction. And so I want to motivate that idea by thinking about what goes on under the hood in many, many recommender systems. So when you or I open up Amazon, we get like a bunch of different things pop up. It's not empty. And so it pops up and gives us recommendations based on what the website thinks we might like. So think about the algorithm that's running in the back end. It knows who you are, it knows where you live, it knows how many credit cards you have, what your past purchases were, and it's using that information to basically select from its gigantic catalog of all the possible things you might want to spend money on, and it's sampling from that, and it's showing you a sample of what the algorithm thinks you're interested in right now at like 2 p.m. on a Saturday. And the same is true in Netflix. So if you open up Netflix, it's not just empty. It's not a search box that tells you what are you feeling like right now. It gives you options. So you should ask yourself, how are those options being generated and what's going on under the hood? And so that's really the kind of problem that we're going to try and think about in what happens in the next hour or so. And we'll think about this in the context of a problem known as matrix factorization. And so the Netflix problem is the problem of movie recommendations. So if you think about what Netflix data scientists have to deal with, they have data that looks like this. So these are different kinds of users that they have based on some of the information the users have given them. And each user or each kind of user might watch a movie. And after they watch a movie, they give the movie the rating. And so this is back when Netflix first kind of came out. You could give a movie or anything you watched a rating from 1 to 5. Now it's just the thumbs up or thumbs down. But back then, you could give it a star. Like 1 star sucks, 5 stars amazing. And you could do this, and this is the data that they would actually have access to. Because users rate only a few items, so you or I might watch 10 movies in the course of like a semester, we're not going to watch the entire catalog of Netflix and give it a rating. So Netflix only has access to a small subset of ratings that each user gives out to every movie. And it's not every movie, to the movies that they actually watched. And so they wanted to solve this problem of how do I get a recommender system going when my data is half missing. So about 10 to 15 years ago, there was a challenge that was put out by Netflix for $1 million called the Netflix Prize. And this actually is sort of a lot of the inspiration for the website Kaggle, which was the idea that Netflix at the time said, we don't know what the best way to solve this problem is, so let's just put it out to the community at large and let people solve it. So they put out a giant data set of their own ratings and movies, and they asked people to find out what the best possible way for them to build a recommender system actually was. And this team won the prize. They had a metric that denoted success. And the interesting thing here is that just by crowdsourcing the solution, they were able to find several high quality solutions that eventually ended up in their production level systems. So this problem is really, really important to lots of companies out in Silicon Valley who want to make sure that people are given good recommendations. Because if people are given good recommendations, they stick around, they spend money on the website. That drives up their own revenue. So that's the incentive structure that these companies have to solve the recommender systems problem. And so what does that have to do with anything we've studied so far? So let's try and move from the algorithm that we learned about in the last hour, PCA, to a more general algorithm called matrix factorization. So in PCA, each input vector was being approximated as its reconstruction, which was equal to the mean plus u times the code vector. And so U is a d by k orthogonal matrix, and Z is the code vector. So let's just, for simplicity, assume that this is mean 0 and data is centered. And so we can write xi as u zi for each data point I. So I've done nothing here. I've just said the data is mean centered, and so each xi is approximated by u zi. Well, I can take all of my xi's and pack them into my data matrix to get an n by d matrix. And I can do the same thing for the z's that I get from PCA. So I take all z1, z2, all the way to zn, and I pack them into this giant matrix Z, which is going to be in n by k. So I have n data points. Each of them has a k-dimensional code vector. When I pack them, it ends up as an n by k dimensional matrix. And in this view, I can write the squared reconstruction error as the summation over n of xi minus uzi, which is equal to x minus z u transpose. And so if we view this from the perspective of matrices, then the summation over n turns into this Frobenius norm. So just as you have L2 norms over vectors, you also have norms over matrices. And the Frobenius norm is one such norm. So the Frobenius norm of a matrix Y, or Y transpose, is basically summing up over all the ij entries and squaring each entry. That's just a definition of the Frobenius norm, which is equivalent to the norm squared of each of the rows of the matrices. Okay, what did I just do? I said PCA is solving, PCA can be thought of as solving this approximate matrix factorization problem, where our goal is to find these factors for our original data matrix. One factor is Z, which is the codes for each of the individuals, and the other factor is U, which is the projection space. And so PCA X is approximately trying to find two matrices, Z and U transpose, or equivalently X transpose is equal to U times Z, where you have X transpose as a D by N matrix, and we're trying to approximate a D by N matrix as a D by K times K by N matrix, where our matrix U, remember, is D times K. So we have K different orthonormal eigenvectors that all get packed together in U. And if we apply the matrix U to each of the data points, then we get Z transpose, which is a K by N K by N matrix, where for each of the N data points, we have a K-dimensional code space. And so based on the size of these matrices, this is what's referred to as a rank N approximation. So in mathematics, you can ask, how do I approximate a matrix? One way to approximate a matrix is via a low rank approximation. And in this particular case, it's a rank K approximation of the original data matrix X transpose. So that's what PCA is doing. It's finding a rank K approximation to X transpose. And so since U was chosen to minimize reconstruction error, because this matrix U transpose was not chosen randomly. It was chosen based on the basis of some objective function, in this case reconstruction error. We say that U and the solution to PCA is the optimal rank K approximation in terms of this objective function. So PCA is finding a rank K approximation to our data matrix based on minimizing the Frobenius norm between the original data matrix and its rank K approximation. This is just restating what we talked about in the previous hour in terms of the problem known as matrix factorization. But PCA is not the only way to factorize a matrix. You can also factorize a matrix using a strategy known as singular value decomposition. And so this has a close relationship to SVD. And so in SVD, you factorize a matrix as U sigma V transpose. And I won't go through a lot of the properties of a singular value decomposition of matrices. I'll leave the slide up for you to read. But the key thing to take away is that it's possible to show that the first n singular values in singular value decomposition correspond exactly to the first n principal components. Or rather, it's possible to show that Z in the PCA projection is equal to U times sigma, where sigma is this sigma and not the covariance matrix of the data. Okay. So why do we care about these matrix factorizations and what PCA does? Well, we saw that PCA gives the optimal low-rank matrix factorization to a matrix X. The question we want to ask is whether we can generalize this to an arbitrary matrix where X is only partially observed. So in the Netflix problem, you have users, N, and you have movies over D dimensions. But not all users rank all movies. So X, your data matrix for Netflix, is only partially observed. So if we want to find a approximate rank K, if we want to find a rank K approximation to a partially observed matrix, how might we do this? So in a sparse 1,000 by 1,000 matrix, where we only have 50,000 observations in that sparse matrix, we might think that it's reasonable that data can be fit using a rank 5 approximation. So if we had a 1,000 by 1,000 matrix, so that's 10 to the 6 numbers in this matrix altogether. If we were to fit a 1,000 by 5 and a 5 by 1,000 matrix, then in total we'll have 1,000 times 5 times 2, which is equal to 10,000 numbers on the right-hand side. So it seems reasonable for us to think about a low-rank approximation to sparse matrices. And so for the Netflix problem, we have a matrix that kind of looks like this. So, we have a ratings matrix where we have users by n you have n users by m movies, and users rate some movies, and we have this R user movie matrix. And the task is to think about predicting missing entries, which is how might a user have rated a movie that they hadn't previously seen. So under the hood, Netflix is trying to solve this task. They want to know, for a movie that a user hasn't seen, what rating could they have given it? Because if they had access to that number, then they could sort their portfolio when you log in, and then just show you the movies that you might give a high rating to as a recommender system. So that's why they want to solve this problem. The problem is that the original data itself that they have to train this low-rank approximation is very, very sparse. And so in the current setting, what they're going to try and do is solve this problem using numerical methods. So we have our original matrix X, which is n users by D movies. And what we're going to try and find is an approximation to it where we have two matrices that we end up with. The first one is what's called a user matrix. And this user matrix has dimensions n by k. And the second one is going to be called the movie matrix. And the movie matrix has dimensions k by d. And the reason we call the first one the user matrix and the second one the movie matrix is because each row of the user matrix and each column of the movie matrix end up being multiplied with each other via dot product in order to generate different entries of the original data matrix. So think back to the idea of a low-dimensional representation. What we're trying to do in a matrix factorization form is to create a factorization of both the users as well as the features into some low-dimensional, some rank k representation. Because what we want to do is attempt to explain the ratings by characterizing both users and movies on a number of factors k that are inferred from the ratings patterns. We seek representations for both movies and users as vectors in RK. So if I had a way to create these vectors in RK for both users and meetings, then what I could do is for each Rij, my ratings matrix, I could do Ui transpose, if this is the movie vector for J, Mj. And by taking the dot product between them, I could believe that I was computing what the rating would have been for user I for movie J. So this is a bit of a tricky thing here that we're discussing, because we started from the problem of matrix factorization. And what I said was that in matrix factorization, you take this n by d matrix and you factorize it into two matrices, one n by k and another k by d. And my claim here is that when you do this factorization, what you're implicitly trying to find are k latent factors that are shared by both users and movies. So what might be a reasonable latent factor that's shared in the context of a Netflix problem? So think back to the experiment in psychology and how people answered questions. So in that case, we found that there were latent factors corresponding to people's agreeableness, how the degree of extroversion. So what might latent factors be here between movies and users' ranking of them? So what might latent factors for movies be? Yeah. Yeah, genres. So you could also think of factors like, so for example, is a movie, how much horror does a movie have? Could be one of the factors that are latent in such a data set. Another latent factor might be the length of a movie, like a really short movie versus a long movie. A third latent factor might be the amount of humor in a movie or the amount of action. And so you can create these hypothetical constructions of what the different latent factors in a movie could be. And for a single user, a user might have preferences over those latent factors. Like I might really enjoy action movies, but someone else might really enjoy dramas. And so these preferences might be expressed at different numbers on each of those k dimensions. And the intuition for matrix factorization is that if I could get a preference vector for my user that tells me how much a single user I prefers a particular latent feature in any movie, and I had another movie vector which tells me how much of this latent vector is manifested within that particular movie, then I can get the rating and I can approximate the rating by just taking the dot product of the two. Yeah.
You mentioned things like how much humor a movie has. How do you quantify something like that?
So you can't really quantify it. I'm giving you an example for what a hypothetical latent representation could look like. You don't actually have annotations for humor. And so, I mean, in practice we do, but we're pretending that we don't. So the goal is to try and uncover these latent factors automatically from the subset of movie ratings that you do have. And what I'm telling you is that the problem of matrix factorization tries to do this automatically. Because when we factorize this matrix, we're trying to find low-dimensional factors for each of our users and simultaneously for each of the features that we have, which in this case is movies. And so I'm trying to give you an intuition for what those factors might look like if we were working in the context of Netflix and movies. And so we can associate these factors, the dimensions of the vectors, with idealized concepts. So this is not what actually happens. This is what we believe could be learned automatically by the matrix factorization problem into things like comedy, drama, action, and a bunch of other uninterpretable dimensions. So if we were able to solve this successfully, the question is, how does that help us? So can we use the sparse matrix R, which is the actual observed data that we do have, that Netflix has, to find these latent factors for all users and all movies successfully? So I'll stop here to see if folks have any questions about this idea of matrix factorization, what these representations K represent, and why it's difficult to actually find it in the context of the Netflix problem. Yeah. No, so for each movie, you're going to have a movie vector, and that's going to be k-dimensional.
So for each movie, you're going to have a vector that's like a rating of like how good.
That's right. Yeah, and you want to find that automatically.
Sorry, I meant like each individual vector.
Yeah, you're going to find each individual vector for all movies and the vector for each user as well, simultaneously. And that's what this matrix factorization is actually doing. So let representation I in the k-dimensional space be UI for each user, and let representation of movie J be ZJ. So the first entry of UI could say how much the user likes horror films, and the first entry of ZJ could be how much movie J is like a horror film. And so you could assume that the rating user I gives to movie J is given by a dot product of UI times ZJ. So this is saying, it's over the k dimensions here of UI k, ZJ k. We're saying the actual rating can be expressed as a linear combination of how much the user likes a particular latent concept times how much a movie expresses that latent concept, summed across all of the different latent concepts. And in matrix form, if we pack all of the vectors U and pack all the vectors Z as Z transpose, then we can write our ratings matrix as U times Z transpose, which is a matrix factorization problem. And in PCA, we saw that to solve a matrix factorization problem optimally with respect to the Frobenius norm of the difference between the original matrix and its factors and the product of its factors, you need to observe all of X. But the problem in the Netflix case is that most of the entries of X are going to be missing. So how do you actually solve this problem? The idea that we're going to use is that we only want to count the error in terms of this Frobenius norm for the entries that we do observe. What does that mean? So let's think about the intuition for this loss function. So this loss function is a Frobenius norm of the difference between two vectors. But it's a Frobenius norm, which means it's summed up over all ij. But we know that we don't observe all ij, we only observe a subset. So let's write this equation down for only the subset of entries in the ratings matrix that we actually observe. So let O of n comma m be the subset of entries in matrix R that are actually observed. And then under the squared error loss, the matrix completion problem requires solving this optimization problem. So we want to find two factors, factor u and factor z, to minimize the summation over I, j, and O. So these are the observed entries of our ratings matrix of Rij minus U transpose I Zj. So these are the parameters of our unsupervised learning problem now, and this is the loss function for matrix completion from partially observed matrices. So any questions up until here? Remember, whenever you see something like this, always just write it out in really simple terms. So let's say we have 3 users in 2 movies, and we observed a 5 here, we observed a 3 here, and we observed a 1 here, and we just don't know what these numbers are because those users never saw those movies. Then the summation of I, j, and O is going to sum over the difference between, it's going to be 5 minus ui transpose zj plus 3 minus u with the I and j corresponding to the correct row and column entries. So the objective above is non-convex in both u and z, which is to say that you're not going to be able to find a global optima to this objective function. Because if you actually care about solving this objective, and you care about optimizing over u and z jointly, but that objective is non-convex. But it turns out, as a function of either u or z, the problem is both convex and very easy to optimize. And in fact, there's a very simple algorithm, and it's called coordinate descent. Because if you squint at this objective, and you fix the values of zi at any given iteration, and you look at what this objective is actually doing, it's saying, I have some Rij, I need to find some U transpose, and I have some Zj that's available to me, minimize the squared norm over a list of entries. And so this is nothing more than the mean squared error for a regression problem, where if we swap out the Rij with Ti, and we swap out the Ui with W transpose, and we swap out the Zj with Xi, it starts to really look like a regression problem. And we know that we can solve regression problems very easily because regression problems, when posed with the mean squared error, are convex optimization problems. And so we can find the global solution for that problem. So we're going to solve this overall problem by breaking it up into 2 subproblems, each of which is convex. And by iterating between 2 solutions of convex optimization problems, we're going to try and solve the overall globally non-convex problem. So the algorithm is called alternating least squares. And so we want to minimize the squared error cost with respect to the factor u, and the case of z is exactly symmetric. So we'll write this squared error term. We'll first distribute this over each of the rows of the rating matrix, and for each of the rows of the rating matrix, we only care about minimizing the jth entries in observed columns. And so this, for every single row of the matrix, only depends on a single term ui. And so what we can do is solve n different regression problems simultaneously or in parallel. And for each regression problem, for each ui, the optimal solution is just zj transpose inverse summation over Rij zj. And this you should think of as an analog to x transpose x, x transpose y, which is the solution that we had derived to a linear regression problem when you want to regress onto y from x. And so the alternating least squares for the matrix completion problem is basically initialize u and z randomly. So these are your 2 factors for your matrix. and then you're going to repeat until convergence. So the first thing that you'll do is solve for ui for each of the i's. So for each of the rows of over your n users, you'll find what the optimal choice of ui would be, keeping the random choice of the Z matrix fixed. Then across all the different movies, you would find the movie vectors one after the other by solving a regression problem again. Yeah.
In practice, do you just end up with sorry, because I was thinking that if you were to actually do this, my guess is that where you end up would have strongly depend on where the calculations are affecting parameters. So very easy affecting parameters.
That's a good question. People often use strategies like random restarts in order to assess the sensitivity of algorithms like this to the initialization points. Random restarts, yeah. So they randomly initialize it a bunch of times to try and find one that, like, basically fits the best in terms of mean squared error with respect to the observed entries. That's one strategy. Again, like, you have a hyperparameter here, which is k, which is the rank of the low rank factors. And so that hyperparameter is typically tuned via, again, a validation set while learning with this algorithm. Okay, and so with that, we're sort of moving on to the last part of today's class. So maybe before we move on to nonlinear representation learning, I want to see if folks have any questions about matrix factorization. So just as a big picture, here's what we covered today. So when we started out, we talked about the problem of learning representations. We wanted to figure out ways to learn representations that were lower dimensional. And we started with the simple case of linear projections. And so to project onto a linear surface, we said that every linear surface can be represented as a linear combination of its orthogonal basis. And we projected onto each of the basis vectors to get this representation code that told you where in that subspace this point lie. To find this subspace, you would have to solve an optimization problem. You'd have to find a subspace that minimizes the reconstruction error, which we proved was the same as maximizing the variation along the projections in this subspace. And what we also showed was that the best strategy to find the subspace was simply to take the covariance matrix and do an eigendecomposition on it and pick the top k eigenvalues. So that's what gave us the eigenvectors, which when we packed together formed this matrix U, this d by k dimensional matrix U, that represented the subspace in its entirety, because every point on that subspace could be represented as a linear combination of all of the column vectors of U. So now that we had that linear subspace, we began thinking about the general problem that PCA was actually trying to solve, which is matrix factorization. Because what PCA did was find the optimal matrix factors U and Z transpose that minimize the Frobenius norm between X, the original data matrix, and the product of U and Z. And there were scenarios like the Netflix challenge where we wanted to solve the exact same problem, but we couldn't because not all of the entries of the data matrix were actually observed. And so in the second half of today's lecture, we ended up coming up with a heuristic solution, an approximate solution for this matrix factorization problem that involved an algorithm called alternating least squares. And so instead, because the exact Frobenius norm was not accessible to us, we approximated it using the observed entries of the data matrix. And that cost function could be solved locally via this algorithm that we just learned about called alternating least squares. So that's the sum total of what we've covered so far. And now what we're going to talk about are mechanisms that we can use to learn nonlinear representations. And so in order to do that, I need to introduce to you a new kind of neural network. And that's called an autoencoder. So an autoencoder is a feed-forward neural net whose job it is to take some input X and learn how to reconstruct X. Not in some lower dimensional space, but in the original space itself. So you're going to take X and try to predict itself. So that's why it's called an autoencoder. To make this non-trivial, because there's a really simple solution to learn how to predict something, which is to learn the identity function. To make this non-trivial, we need to add a bottleneck layer whose dimension is much smaller than the input. So let's see what that means by looking at what the forward pass looks like for an autoencoder. Let's say we're working with MNIST digits, so we have a 28 by 28 input image X, which is, when flattened, a 784 dimensional vector. So in the first layer, we have a 784 dimensional set of inputs that we multiply with a 784 by 100 dimensional weight vector to get 100 dimensional hidden units, and then we apply a nonlinearity to get a hidden representation that has 100 dimensions in size. Then we multiply by another matrix that has 100 and times 20 in dimensionality to get the code vector for this input data point. So at this point, we've taken this input, we've applied a linear function and a nonlinearity, and then we apply another linear function and potentially a nonlinearity to get the code vector. And this code vector has exactly 20 dimensions in it. So we've compressed our data from 784 dimensions onto 20 dimensions only. Now, we're going to decode it. So this process of going from the input to the code vector is what is called an encoder. So we're going to decode this input, which is to go from the code vector back to its reconstruction. To do that, we're going to first multiply by a 20 by 100 dimensional matrix in this layer to go to 100 hidden units. And then again with a 100 times 784 dimensional matrix after a nonlinearity to create a 784 dimensional output vector. And that's going to be x tilde, our reconstruction. So that's how we go from here to this code vector z back to the reconstruction via the forward pass of a neural network. And the first part is called the encoder, and the second part is called the decoder. So this is just a feed-forward neural network, and you can train that feed-forward neural network by minimizing the reconstruction error. And you can do this across all of your n data points. So why do this at all? So one reason might be visualization again. You want to learn nonlinear mechanisms to map from high dimensional data onto low dimensional representations. And the second is to learn abstract features in an unsupervised way so you can then apply them to a downstream supervised task. So if you don't have a lot of labeled data, you might think that a good algorithm that learns to reconstruct data exactly as it is can only do so by learning interesting or salient features that exist in this high-dimensional data set. And your hypothesis is that those compressed representations that you learn in those code vectors in the bottleneck layer help you build predictive models that generalize better. And so the simple kind of autoencoder has one layer, linear activations, and a squared error loss. So let's think about what happens to an autoencoder when you remove all the activations and you only have one layer in the encoder and another layer in the decoder. So it's the simplest kind. So in this particular case, this network is computing the function W2, W1, X. So this is your first linear layer, there's no activation, and then you apply that output to your second linear layer, again no activation, and that's exactly your reconstruction. And now you're going to minimize the reconstruction error. So if k is greater than or equal to d, we can obviously choose W2 and W1 such that the product of the two is the identity matrix as our solution to linear autoencoding. But if k is much less than d, then W1 maps to a k, maps x, every input x, to some k-dimensional space, so it's doing some form of dimensionality reduction. And we can ask the question, what is it learning? So we can observe that the output of the autoencoder must lie in a k-dimensional subspace spanned by the columns of W2 because you can write every reconstruction X as W2 times Z, where Z is your code vector. And this is nothing more than writing out your output of, or your reconstruction as a linear combinations of the columns of W2. That's what multiplying by the matrix, left multiplying by a matrix does. So you can write down that the output must lie in a k-dimensional subspace spanned by the columns of W2. And we've previously showed that the best possible minimum error k-dimensional linear subspace can be achieved by the PCA algorithm. And so the autoencoder does this by setting W1 is equal to U transpose and W2 equals U. And so the optimal weights for a linear autoencoder essentially correspond to a principal component analysis. So it's important to note the difference between these two algorithms. So with a linear autoencoder that has one layer, no activations, you can learn those weights, W1 and W2, and you learn U and U transpose. But the mechanism that you use for learning is not eigendecomposition. It's gradient-based learning of the eigenvectors of the covariance matrix of your data set. That's what's happening when you train this linear autoencoder versus getting the solution directly from PCA. So it's really important to understand that even though at optimality these two models yield the exact same solution because they are one and the same, the mechanism of learning between the two is very different. But the much more interesting and relevant case shows up when you have nonlinearities. So you have a deep nonlinear autoencoder that learns to project the data not onto a subspace, but onto some nonlinear manifold. And so this manifold is going to be the image of the decoder. So when you have nonlinearities in your autoencoder, you're doing some form of nonlinear dimensionality reduction. And you can compare and contrast what PCA does. So this is what PCA of MNIST images look like when you have 30 dimensions in your in your projection. So you kind of get a gist, like you can guess what these numbers are, but it's very blurry. And you can do the exact same thing with a 30-dimensional nonlinear autoencoder. And you'll see that it captures much sharper features using just 30 dimensions. Remember, the original dimensionality of the data is 784 dimensions. So you can actually train this very, very quickly on a Colab just to see what it does, because you already have the MNIST data set. And so finally, I think that these nonlinear autoencoders can also be applied to other data sets like text data. So imagine if you had very, very large corpuses of text data where each document was represented as a vector of words, and you counted the number of words that existed across your document, and that was your features. You could run an autoencoder on that data and visualize the code representation. And it turns out that the code representation sort of naturally clusters according to the metadata in the article. So you have information on monetary or economic documents, you'd see that, or on energy markets, you'd see that. Yeah, you had a question?
What would the advantage be using PCA over another?
So PCA is you get the solution directly. Like you don't have to wait for gradient descent to converge. You know that it's the optimal solution, and you know that that's what gradient descent is going to do. And there's very, very fast algorithms for finding eigenvectors of matrices. They do come at an additional cost, though. So like you need to be able to like actually represent your covariance matrix in memory. So that's maybe like one of the trade-offs to consider. But yeah, that sort of represents all the topics that I wanted to tell you guys about dimensionality reduction. I think the really, really interesting thing that you should take away from this is that this starts to get at a concept we talked about at the very beginning of the semester, which is that data don't always exist in this high-dimensional space. They lie on some low-dimensional manifold. And really what all these methods are trying to do is impose different kinds of assumptions on the model to find that underlying manifold. Like PCA makes the assumption that your manifold is a linear subspace. but autoencoders make the assumption that it is a nonlinear manifold that is representable and learnable via a neural network. So depending on the kind of assumptions made, you get different results, but this principle of representation learning, or this principle of finding a good representation of the data, is just a very powerful one. It's used all across machine learning. And so most of the methods that you see in practice right now make use of this idea in some form or the other. Okay, so that's most of it for today. And if you have any questions, I'll stick around for a bit. But thank you. Oh, just a small announcement. We'll have a ethics module. I believe it's next week. And so please do come by in class for that, because your participation grade really, really depends on you actually filling out some of the content that we'll have in class.